Good morning or good afternoon. Today, Ariana Torres, Francis Gonzalez, Pedro Vega, Esteban Bermudez, and I, Alexandra Juan, are going to be discussing thermal radiation. In this picture, we see a fireplace where thermal radiation would be the heat felt in the room. Some other examples of radiation in our everyday lives are ultraviolet light from the sun, heat from the stove. Almost any process that requires heat transfer depends crucially on the radiating properties of the materials used. This is why the study of thermal radiation is important for working in the industry. Our agenda for today will be the following. Goals and objectives will be discussed by Alexandra Guan, as well as half of theory. Then, following, Esteban Bermudez will discuss half of the theory left. Equipment description and experimental procedure will be presented by Francis Gonzalez. Experimental design by Ariana Torres. The data analysis and the work plan by Pedro Vega. In order to study thermal radiation, 5 experiments were performed. The overall goal is to study the effects of radiation heat transfer by establishing test parameters and perform different experimentations where these parameters are changed. The objectives for the following 5 experiments are: for the Stefan Boltzmann experiment, it is to determine the heat transfer by radiation for the matted black plate by applying different magnitudes of voltage to the system. For the inverse square law experiment, it is to determine how radiation heat transfer is affected by distance. For the cosine law experiment, it is to determine how thermal radiation is affected by the angle of the incidence. For the emissivity experiment, it is to determine emissivity of different surfaces using the emissivity of a matted black plate as reference. And last but not least, for the cylinder unit experiment, it is to determine heat transfer by radiation with known surface area and emissivity, and to determine emissivity of the other cylinders with different surface materials. What is heat transfer? Well, heat transfer is the science that seeks to predict the energy transferred between material bodies as a result of temperature difference. There are 3 types of heat transfer: radiation, conduction, and convection. To the left, we can see a picture of a coffee cup. Here, radiation would occur by reheating the cold coffee in the microwave or the warmth you feel from the coffee. That is not because you are touching the cup of coffee, just because you have the coffee close. Conduction is the heat felt in your hands from the cup, and convection is the heat that leaves the cup as the currents of steam and air rise. To the right, we can see that when a temperature gradient exists in a body, we say it transfers from a region of high temperature to the low temperature region. Radiation is the transfer of heat through electromagnetic waves through space. As opposed to heat transfer processes like conduction and convection that require matter to transfer heat, electromagnetic radiation is a method of heat transfer that does not rely on any contact between the heat source and the object being heated. No mass is exchanged and no medium is required. The electromagnetic radiation propagated as a result of a temperature difference is named thermal radiation. When a solid body is heated, the surface of the solid emits thermal radiation. This happens because when energy is supplied to a solid body, some of the constituent molecules and atoms are raised to excited states. When the atoms or molecules return to their lower energy states, energy lost as the molecules move from energy states is emitted in the form of electromagnetic radiation, which is distributed over a range of wavelengths. The various kinds of radiation are distinguishable from one another only by the range of wavelengths they include, as seen in the picture on the right side of the slide. Thermal radiation ranges from 0.1 to 10 microns. In a vacuum, all these forms of radiant energy travel with the speed of light c equal to 2.99 times 10 to the 8th meters per second. The wavelength, lambda, characterizing an electromagnetic wave is related to its frequency v by lambda equals c over v. A photon, which is a particle with charge 0 and mass 0, is associated with an electromagnetic wave frequency of V. The energy of this photon is given by E equals h, which is the Planck's constant, times V. We can observe the effect of thermal radiation in the picture where the boy is heating his marshmallow with the thermal radiation emitted from the fire. The Stefan-Boltzmann relationship governs only radiation emitted from a black body. A black body is an idealized physical body that absorbs all incident electromagnetic radiation regardless of frequency or angle of incidence. To be at thermal equilibrium, it must emit radiation at the same rate as it absorbs radiation. A black body in thermal equilibrium and at a constant temperature emits electromagnetic radiation called black body radiation. The radiation is emitted according to Planck's law, meaning that it has a spectrum that is determined by the temperature alone, not by the body's shape or composition. In other words, the wavelength spectrum of black body radiation depends only on the temperature and not on the material it is made out of. The total radiated energy increases as temperature increases as well. The properties of an ideal black body in thermal equilibrium are that it is an ideal emitter at every frequency, and it is a diffuse emitter. The latter meaning the energy is radiated isotropically, which is independent of direction. For this ideal thermal radiator or black body, the energy emitted is at a rate proportional to the fourth power of the absolute temperature of the body and directly proportional to the surface area. This is shown by the Stefan-Boltzmann law of thermal radiation for black bodies, which is that the heat emitted equals sigma times A times T to the fourth, in which A is the surface area, T is the temperature of the surface, and sigma is the Stefan-Boltzmann constant, which has a value of 5.67 times 10 to the negative 12 watts over delta Kelvin to the fourth times meters squared. The net radiant exchange between two surfaces will be proportional to the difference in absolute temperatures to the fourth power, defined as Q radiation equals sigma A times T to the fourth minus T to the fourth.
The inverse square of the distance law is a law that applies to phenomena that work at a distance. For example, electromagnetic radiation, gravity, and electrostatic forces. It is assumed that this energy emanates from a point source. Therefore, that point source exerts its energy or exerts its force at a radius of a sphere to all directions around it. So, the flux can be seen as the strength over the area. For example, in this image here with the arrows and the areas from a point source in blue, we can see that as the distance of the radius gets larger, the flux, or how many arrows pass through each square, gets smaller as a function of the radius of the distance. So as the area increases proportionately with the radius squared, the energy that passes through each unit area decreases with the square of the distance, or 1 over d squared, which is also seen in the graph to the right that shows how the value of y, or in this case the energy, decreases as the square of the distance x. For Lambert's cosine law, we now measure the radiation between two surfaces that are radiating heat. So this refers to the energy radiated by a body that is intersected by another, but that are not perfectly parallel to each other. This is defined by the first equation shown that gives the radiated heat between these two surfaces. F12 and F21 are defined as functions of the infinitesimal areas dA sub 1 sub I, the distances r between the objects, and the angles phi sub I. Integrating a hemisphere over each of the emitting infinitesimal areas, we get the second equation shown, that is a function of the angle phi between the normal vector and the radius of distance between the two surface areas, and this defines the energy emitted by each infinitesimal area dA sub I. Now, integrating over the entire areas, we can get all the energy transferred by all the infinitesimal areas added together from each of the two surfaces, A1 and A2. So the energy transfer between the two areas, Q1, 2, equals the subtraction E sub B1 minus E sub B2. So the subtraction between area 1, the total energy of area 1 and the total energy of area 2, times the integration of the entire area 1 times the integration of the entire area 2. Cosine phi sub 1 times cosine phi sub 2 times the infinitesimal area 1 times the infinitesimal area 2 over pi r squared. Now, to calculate and determine the plate emissivity, we must use the Stefan-Boltzmann relation, which establishes that radiation depends on the area, emissivity, and temperature difference. However, for constant area and temperature, only emissivity varies. Emissivity depends on the surface morphology of what is emitting, which could be rough or a polished surface, and its color, which could be darker or lighter colors, among other variables. As we can see from the graph on the right, a perfectly black body emits all wavelengths completely and perfectly. It emits all the wavelengths that is directed towards it. In the case of a gray body, we can see that emissivity is less than 1, but it still emits most of the radiation depending on how much between 0 and 1 its value is. As we can see, real objects are not perfect emitters. The emissivity is between 0 and 1, and it is a fraction of the emissivity of the real surface over the emissivity of a black body. From the graph, a real surface, we can see that its emissivity fluctuates and does not follow a clear trend, but we can see that it still kind of behaves somewhat like the gray body, but it still varies a lot depending on the wavelength. For the cylinder analysis, heat is generated through an electrical heater in the center of the cylinder. So it is transferred by radiation because of a very high temperature, and the heat generated can be calculated through the power equation, which relates heat transfer or heat generated to current and voltage. So the heat generated is equal to the current times the voltage. The heat due to radiation is given by the Stefan-Boltzmann relationship that has been given before. And the heat due to convection is the balance. So the total heat generated minus the heat lost through radiation is equal to the heat lost through convection. Then the heat convection coefficient can be calculated from this convection energy and solving for H. As we can see from the image to the right, some heat is lost through radiation inside the cylinder, and the rest is lost through convection outside the cylinder and also through radiation.
For this experiment, there will be a thermopile unit consisting of a thermopile and an electric heater, which will be at a certain distance from the thermopile. This distance between the heater and the thermopile was varied along the experiments. Aluminum plates in the heater were heated up and radiation was emitted from the plate. This radiation was then received by a thermopile, thanks to a funnel-shaped reflector that collected and concentrated the radiation. This reflector would intensify the heat by a factor of 20, and the thermopile would then transform this heat into a current, which was measured by a galvanometer. The temperature of the heater was measured by a pyrometer using a thermocouple. The thermopile could be placed directly in front of the electric heater or varying at angles. The desired parameters for each experiment using the thermopile unit were manipulated with the use of a control panel. For the Stefan-Boltzmann part of the experiment, the selector switch in the control panel was adjusted to 7, and the low TC selector switch was moved to 12. A black matte square aluminum plate was installed in the heater and aligned with a thermopile aperture. The heater was then moved 10 inches away from the thermopile and placed in the 0-degree configuration. The variable transformer was adjusted to supply 50 volts to the heater, causing the 15-volt indicator light to turn on. When the temperature readings in the pyrometer were stable, the values for millivolts were generated. Pyrometer temperature and ambient temperature was collected. The same procedure was performed, adjusting the variable transformer to 60 volts and 70 volts. For the inverse square law part of the experiment, the selector switch in the control panel was adjusted to 7, and the low TC selector switch was moved to 12. The black matte square aluminum plate was installed in the heater and aligned with a thermopile aperture. The heater remains 10 inches away from the thermopile with no variation in its angle. The variable transformer was adjusted to supply 50 volts to the heater, causing the 15-volt indicator light to turn on. When the temperature readings in the pyrometer were stable, the temperature in millivolts were written down. The procedure was repeated 2 more times, with changing the distance from the thermopile and the heater to 16 and 13 inches. In all these readings, the temperature had to remain constant. If the temperature varied, the run had to be repeated until the temperature remained constant during the readings. For the Lambert's cosine law part of the experiment, the selector switch was adjusted to 7 and the low TC selector switch was moved to 12. The black matte square aluminum plate was installed in the heater and aligned with a thermopile aperture. The heater remains 10 inches away from the thermopile, and the variable transformer was adjusted so that it supplies 50 volts to the heater, causing the 15-volt indicator light to turn on. When the temperature readings in the pyrometer were stable, the temperature, millivolts, and the thermopile angle were written down. Initially, the angle is kept at 0 degrees. The thermopile is moved so that it has an angle of 15 degrees with respect to the heater, and a mask marked 15 degrees is installed in the thermopile. When the temperature readings in the pyrometer were stable, the temperature and millivolts were written down again. This procedure was repeated for an angle of 30 and 45 degrees, also installing the mask on the thermopile corresponding to 30 and 45 degrees. For the emissivity part of the experiment, different plates were installed onto the heater. The plates used for this experiment were made out of aluminum with a 2.5-inch square surface that was coated with different pigments. These pigments were white, red, aluminum, matte black, and a plate that had no pigment. The selector switch in the control panel was adjusted to 7, and the low TC selector switch was moved to 12. The heater is kept 10 inches away from the thermopile with no variation in its angle. The transformer is adapted to apply the same voltage to all of the plates. When the temperature and millivolt readings were constant, these were recorded in triplicate, and it was taken into consideration that for the matte black plate, an emissivity equal to 0.95 was presumed in order to calculate the other plate's emissivity. The cylinder unit used in the experiment consisted of 5 cylinders installed on an insulating panel. Each cylinder was wrapped with an insulating cover, and the center of each cylinder contained a low-voltage electric heater. This electric energy applied to the heater transformed into heat and was transferred into the interior area of the cylinder by radiation because of the high temperatures. The heat absorbed by the interior of the cylinder was transmitted into the exterior of the cylinder, which dissipated into the environment by radiation and convection. The heat transferred by convection depended on the shape and area of the surface, the velocity of the air currents, and the temperature difference between the surface of the cylinder and the environment. Based on laboratory environment conditions, it was assumed that the air velocity was caused by thermal circulation, making it so that the heat by convection will be the same for every object of the same shape and area. Like in the thermopile unit, the system was manipulated with the control panel. In this experiment, the selector switch in the control panel was adjusted to 1, turning on the light in cylinder 1. Then the high TC switch and the low TC switch were also changed to 1. The transformer was set to 12 volts so that the ammeter would provide 6.5 amps. The internal temperature for cylinder 1 was monitored until steady-state conditions were reached, with the aid of a pyrometer and a thermocouple attached to its corresponding terminal. Once the internal temperature was constant, the data for the voltage, the amperage, the internal temperature, and the external temperature for cylinder 1 was collected. The external temperature would have been measured with a contact pyrometer. The variable transformer was adjusted to 0 and the selector switch to 2 in order to repeat the procedure for cylinder number 2. The procedure was then repeated for the remaining cylinders while adjusting the selector switch to the corresponding number of the cylinder.
For the Stefan-Boltzmann experimental design, we will have 3 different test numbers and varying the voltage of the system in each run. We will be collecting the parameter temperature as well as the millivolts. The variables that remain constant in this experiment is the ambient temperature. The configuration of the thermopile will remain at 0 degrees, and the heater will remain 10 inches away from the thermopile. The experimental design for the inverse square law will determine how distance affects the radiation heat transfer using the inverse square law. So we will be varying the distance of the plate to the thermopile between 10 to 16 inches with each run. We will collect the parameter temperature as well as the millivolts, and the ambient temperature will remain constant. The thermopile configuration will remain at 0 degrees, and the voltage of the system will be 55 volts. The experimental design of the Lambert cosine law will help us determine how radiation heat transfer is affected by the cosine of the angle of incidence. So we will have 4 different test numbers, and in each run, we will be varying the angles of the thermopile from 0 to 45 degrees. We will be collecting the parameter temperature as well as the millivolts, and the variables that remain constant is ambient temperature, how many inches the heater is away from the thermopile, which in this case will be 10 inches, as well as the voltage of the system will remain at 55 volts. The experimental design of emissivity helps us determine the emissivity of different surfaces using the matte black plate as reference. We will have 2 different test numbers, one with the white plate and the second with the red plate. We will be collecting the parameter temperature as well as the millivolts, and the variables that remain constant in this experiment is again the ambient temperature. The thermopile configuration will remain at 0 degrees. The voltage of the system will be at 55 volts, and the heater will be 10 inches away from the thermopile. For the experimental design of the cylinder units, we will have 5 different runs, and this will help us determine the heat transferred by radiation for cylinders 1, 2, and 3 with known surface area and emissivity in order to determine the emissivity of cylinders 4 and 5. What varies in this experiment is the different surface material. In run number 4, we will have copper oxide, and for run number 5, we will have nickel. We will collect the parameter temperature internally and externally. The variables that remain constant in this experiment is the ambient temperature. The thermopile configuration will be 0 degrees. The voltage of the system will remain at 55 volts, and the heater will be 10 inches away from the thermopile.
For the Stefan-Boltzmann experiment, we will be obtaining the generated voltage, the parameter temperature, and the ambient temperature. Using these measurements, we will calculate the heat transfer by radiation for each voltage adjusted by the transformer. Our first measurement we will be taking as the reference, since we want to take it when it reaches steady state. Using this measurement, we then determine the calculated millivolts corresponding to the adjusted voltage of the transformer. For statistical analysis of data, a plot of voltage versus the difference in temperature will be made with both the generated and calculated voltages. A linear correlation of the data must be obtained. For the inverse square law, we will obtain the same data measurements. For determining the calculated millivolts, we will use the ratio of the squared distances using the first measurement as reference and with the rest of the data obtained. For analysis of the data, we plot the squared distance versus both the generated and calculated voltage and see its behavior. we should expect a linear relationship between the data. Since we're using the square distance, we know that it is inversely proportional to the voltage, so when plotting, we will see a negative trend line. Since it's inversely proportional, we then plot the inverse of the square distance versus the voltages, and then we obtain a positive linear relationship. As for the Lambert's cosine law, the calculated millivolts will be obtained parting from the ratio of the cosine of the angles of the thermopile. Since results are mostly affected by the angle, plots of angles versus voltages will be made for relationship of data. Since when changing the angle with respect to the surface of the plate reduces the intensity which radiation is emitted to the plate, we should expect an inverse proportion for the data, being at angle 0 the highest value for the voltage. For this experiment, we will take the black matte plate as reference assumed to be 0.95 for the other emissivities calculations. Calculation for the test emissivities, we take the ratio between the voltage generated of the plate to be tested and the voltage generated for the black plate, and then use the emissivity factor of the black plate. With the values of the emissivities determined, data will be then compared with each plate. For cylinder units, in addition of measurements of voltage and ambient temperature, we will also measure the internal and external temperature of each cylinder and the current applied. We first calculate the total heat applied for each cylinder using the measured current and voltage. For cylinders 1, 2, and 3 with known emissivity, the heat of radiation is calculated. Here, we must take in consideration the area, since the cylinders have different dimensions, thus different areas. For these cylinders, we will then calculate the heat by convection, subtracting the heat radiation heat to the total heat applied. For cylinders 4 and 5 with unknown emissivity, heat of radiation is calculated using the heat of convection of the first cylinder, since they have the same dimensions. Then with this, we can obtain the emissivity subtracting the heat of radiation of the first cylinder to the calculated before, and applying the emissivity factor of reference. When obtaining this data, we can compare the heat of radiations and emissivities for each cylinder with the change in dimensions and the change in surface material. The work plan for this experiment on the first day, we're doing right now the radiation experiment presentation. After being approved, we will then start the Stefan Boltzmann section, and then finish the day with the inverse square law. In our second day, we will then start with the cylinder units experimentation, then do the Lambert's cosine law, and finish the experimentation with the emissivity section. And on our third day, we will then submit our experiment report.
Here are the works cited for this presentation.